everyone, Mrs. Patel Dane here with topic 7.13, pH and solubility. So here we're going to look at the qualitative effects of changes in pH on the solubility of a substance. So if you think back to topic 7.11, we showed you this glass that had this film on the bottom, and no matter how much scrubbing I did, there was no way of getting that out. But when I added a certain substance to it, it automatically kind of dissolved in that substance, and then the glass became clean again. So today we're kind of answering why that happened. So first, we need to look back at acids and bases and what that means. So if a solution is basic, it means that it has more hydroxide ions, and its pH is going to be greater than 7. If it's acidic, it has more hydronium ions or hydrogen ions, and its pH is going to be less than 7. If it's neutral, well, when you have the same amount of hydrogen ions and hydroxide ions, you end up with water, which is a pH of 7. One thing I want to make sure we caution you guys about is that a lot of times people think, oh, if something's really basic, like a pH of 14, it's not as dangerous as something that's acidic. It's still going to damage your skin. Just that we always say that acidic means that it's going to damage it more, not necessarily. So we're going to look first at strong acids versus weak acids and what they mean. So strong acid means that it's going to disassociate completely, meaning break apart completely, versus a weak acid doesn't break apart completely, and that ends up forming an equilibrium. So if we look at the strong acids, there's the big six, which you should memorize, you should know. But if look at the periodic table to see kind of the relationship between chlorine, bromine, and iodine. Probably see that trend right there in your group 17. And then we also have HNO3, nitric acid, sulfuric acid, and HClO4. So again, make sure that you memorize those six. You need to make sure that we have those. So pretty much what that means when they're a strong acid is that when we have this in solution, it's going to, again, break up completely. So if you have HCl, they don't stay together as an HCl molecule. Instead, when it's added to water, it breaks up into H plus ions and Cl minus ions. So we don't see an equilibrium shift in there. So if we look at the other ones, we see that this is how they break up. Notice that this is an arrow that goes straight into the products. So we want to make sure that you see that they, again, do not go back towards the reactants. If we think about our weak acids, on the other hand, they do not disassociate completely. So you're going to have some reactants and some of the products. So here are some of the examples that we have here, and we'll show you some more in just a bit. So what happens here is that you have, in this case, hydrogen carbonate is in equilibrium with hydrogen ions and carbonate ions as well. So again, notice the difference in the arrow. Strong acids, you show the straight up arrow that goes in one direction. Weak acids, you show this in equilibrium. So again, these are examples of other basic ions that you might see. So any of these attached to some of our cations. So this is what happens. Say we have magnesium hydroxide. It's a weak, essentially you see this in equilibrium, sorry. So you see Mg plus 2 and 2 OH minus. So if we were to put this into a seesaw for Le Chatelier's principle, again, this is what we would see. Now we're going to add an acid to it. So again, when we say we add an acid to it, it's anything that has an H plus in there that's going to disassociate. So when we're just going to put in the H plus, again, it's going to disassociate completely, so we're just seeing the H plus. Well, when you have OH minus and H plus, think about what you make, right? We end up making just water, pure water. So that is going to be taken up, the OH minus, is going to be taken up into making water. So we're essentially going to decrease the amount of OH ions. And when we think about what happens with equilibrium, or in our seesaw, we see that it shifts towards the products. So if you had a magnesium hydroxide that caked onto a container and added a little bit of acid to it, you see that the magnesium ions and the hydroxide ions will disassociate. So you see less of the solid on your container and more of it in solution that can then get washed down and washed away, essentially. So the equilibrium, again, shifts towards the products. So here's some practice problems. We have 5 different examples here, and we want to see which ones are more soluble in water or in acidic conditions, and justify using Le Chatelier's principle. Don't forget to take a look at those big 6 to see if any of them fall into here when you add an H plus in. All right, so let's take a look at the first one. Here we have sodium acetate. Those of you that like salt and vinegar chips, that's the vinegar that you taste. That's that taste that you have there. That's the sodium acetate. So we know it breaks up into Na plus and the acetate ion. When we add an acid to it, we're adding the H plus, and so we see that these two will combine, and they're not part of the big six, meaning that they are going to be a weak acid. So we're going to see HC2H3O2 in here. So when we think about our equilibrium and our seesaw, well, we're going to take up some of that acetate ion. When we do that, we see that our equilibrium will shift towards the right-hand side. Taking a look at B, you have CuI2 is in equilibrium with Cu plus 2, sorry about that subscript error, plus 2 iodines, and again, those are aqueous solutions. When we add H plus to this, we see that those two will form HI, which is part of our big six, meaning that we see a forward arrow, we don't see this in equilibrium. So we're going to see in Le Chatelier's principle that we're going to end up having more iodine ions present. And so we're going to actually favor, when we see more iodine ions, we're actually going to favor the left-hand side or favor the reactants instead. So this would not dissolve very well in acidic conditions. When we think about the other three, so we've got PbCO3 is in equilibrium with Pb plus 2 and CO3 minus 2. Well, when we take that CO3 minus 2 and add that to an acid, H plus, we see that it forms an equilibrium, the hydrogen carbonate that you had seen before. And so we don't see that, we end up taking up more of that CO3 minus 2 ion. And this equilibrium will shift towards the right. Magnesium hydroxide. So Mg plus 2 plus 2OH minus, we again see that shift towards the right. So we see that more of it will dissolve in an acid. For E, your calcium sulfate, which produces your calcium ion and your sulfate ion. When you take that sulfate ion and add that to water, well, that forms sulfuric acid, which is one of the big six. And so that won't dissolve very well, essentially. So now, can you qualitatively determine the effects of changes in your pH when it comes to the solubility of a salt? Thank you for watching, and hopefully you have a great day.